Okay, then we can start our lecture tonight. So tonight we will talk about our third lecture, which is about the internal loadings developed in structural members. Well, actually, this one we'll talk about something related to the bending moment, shear force, and then the normal forces. Actually, some of them are being taught before, like in the structural mechanics or mechanics of material. So you should have some idea for that. And then some of the concept you have learned before, and you can treat it as a kind of revisions. And then for the remaining part, we will also talk about the way how to find out the shear force and then the bending moment for frame structures, which is actually new to you, but actually uses similar type of the concept. And then you just apply those in the beams and then to the frame members, and then you can draw the shear force and then the bending moment diagram for the frame members. So here is the chapter outline. So we will talk about the internal loading at a specified point, and then we will talk about the shear and the moment functions. Afterward, we will talk about the shear and then the bending moment diagram for a beam. And then we will also mention about the shear and moment diagram for frame structures. And then finally, we will mention about the moment diagram construct by the method of superposition. So here is the our chapter. So first of all, we will mention about the internal loadings in a specified point. For internal loading or internal forces at a particular point of the member, actually we would consider a member sections. Actually, if you want to find the internal forces at a particular location, usually we will cut through that particular section and then consider the equilibrium. And then we can find a so-called internal loading or internal forces. The internal loadings basically refers to the normal force N, the shear force V, and then the bending moment M. That's actually the letters that we use to describe the normal force, the shear force, and then the bending moment. Normal force, that means either it is tension or compression, while the shear force is actually the force which is perpendicular to the section being cut. Or I can say that it is perpendicular to the axis of the member being cut, or it is actually parallel to the face it is being cut at a particular section. And for bending moment, actually, you know that it is the moment to keep the section in equilibrium. Well, before we go on, we just mentioned about the sign convention of the internal forces. As you can see here, it shows all the internal forces, actually they are acting in the positive directions. For normal forces, as you can see, we usually don't define pointing to the left or pointing to the right as positive, because actually it is very difficult to define is pointing to the left or pointing to the right as positive, as when you cut the member, the force can be both acting to the left and acting to the right. So instead of using direction as positive or negative, we will mention that usually in tension, it is positive normal force. So right here, you can see that when the force is pointing away from the section, so it is actually the tension force. So for here, you can see that this is a tension force, it's pointing away from the section. So you can see that on the left-hand side, it's pointing to the left, on the right-hand side, point to the right. So both of them actually mention about a tension force for a member. So both of them are positive. And then for shear, if you can turn the section into clockwise sense, this one is clockwise sense, then they are positive shear. So you can see that on the left-hand side, if the shear is pointing upward, then it actually can turn the section into clockwise sense. So it is a positive shear. On the right-hand side, you can see that the shear force is pointing downward as positive because it can turn the section in clockwise sense. So you can see that we don't define pointing upward or pointing downward as positive shear, because actually both pointing upward and pointing downwards are positive, as long as it can turn the section into clockwise sense, okay? And then for the bending moment, you can see that again, we don't use counterclockwise or clockwise as positive. Instead, we say that if the moment can make the section to bend concave downward, so you can see that this section is actually under the action of positive moment, and then actually it will be something like that. The section will be bent pointing down, concave downward. Then this is the positive bending moment. But for your easy of memorization, actually it is you can think that actually this is the structures, and then this is the bending moment. When the bending moment can make your structure happy, then it is a positive bending moment. Okay. Well, if a bending moment actually act in the negative direction, that means it is a concave upward, then actually it bend like this, then which actually make your structures unhappy, then we call that it is a negative bending moment. Okay, it is. I think it is easier for you to memorize the sense of positive and the negative for bending moment. Okay, so you may ask, hey Simon, for the equilibrium equation, you always assume that pointing upwards as positive, pointing to the right as positive, and then for bending moment, you assume that counterclockwise as positive. Why you mentioned that we don't use that kind of sense to define the sign convention for our shear force and bending moment? Now, don't mix it up. Actually, that one is for equilibrium equations. This one is the sign convention. They are not. We are not talking about the same idea. Okay. For the sign convention, actually, we define it this way for the positive shear, positive moment, and then positive normal forces. For equilibrium equations, well, if we saying that using right as the positive, or actually we can also use pointing to the left as the positive. As you just need to choose one direction as positive, the other one as negative, then it will give you the same answer. In other words, actually, it doesn't matter. You choose pointing to the right as positive or pointing to the left as positive in the equilibrium equation. It gives you the same answer. And then for vertical force, we use summation of Fy is equal to 0. And then just like what we have mentioned before, you're pointing upwards as positive. But just trust me, when you choose pointing downward as positive, you will get the same answer. And then for the bending moment, again, for the equilibrium equation, we assume that, well, counterclockwise as positive. But if you assume that clockwise as positive, it will give you the same answer. So it's just for equilibrium equation, basically, you will get the same answer. No matter you assume pointing to the left as positive or pointing to the right as positive, pointing upwards as positive, pointing downwards as positive, you always get the same answer. So in the equilibrium equation, you just need to choose one direction as positive, then that's fine, okay? Okay, then the procedure actually to find out the internal force at a specific point is as follows. First of all, actually, you need to find out all the support reactions by using the equilibrium equations. If you have a pin connection, like a compound beam, remember to detach your sections at the pin connections and to expose the support reaction at the pin. And then you have to keep all the distributed loads and then couple moment forces in the exact location. Don't change the location of the forces in the moment. At the section that you want to find out the internal force, then you pass an imaginary section right there. And then we'll create a free body diagram at that particular section. Remember, at the section where you cut, you need to write down or you need to indicate the internal forces like the normal force, the shear force, and then the bending moment. Make sure that they are in their positive directions. And then afterward, you write down the equilibrium equations and then to find out the normal force, shear force, and then the bending moment. Now remember that as you have already put them in their positive direction, if in the equilibrium equations you got a negative answer, that means your assumed direction is wrong. You need to reverse the direction that you have assumed. Okay. So here I give you an example about how to find the internal forces of a particular point. Here is actually, it shows the building roof has a weight of 1.8 kN per meter square and is supported by on a 8 meter long simply supported beam that are spaced 1 meter apart. So you can see that the length of the beam here is 8 meter. And then they are in turn supported by the 2 girders on both sides. And then this is actually the girder. Okay. And then this girder is located at the front and the back of the building. And then determine the internal shear and the moment in the front girder at the point C. So you can see that this is a point C here. We want to find out what is the shear force and then the bending moment here. So we will cut it out and then to take a look what is the shear and the bending moment. Well, you can see that the loads applied on the beam here is equal to 1.8 kN per meter. So the total length of the beam is equal to 8 meter. So from here, you can find out the total values of the force applied on the beam is equal to 15.4. 14.4. So we divided into 2 because it is a simply supported beam. So you have 7.2 kN as the support reaction. So right here, you can see that when you have 1.8 and then you times 8 because the total length is equal to 8 meter. So this is the total loads and then it is simply supported on both sides. And then if you just divide it by 2, so the support reaction on both sides is equal to 7.2. So as the beams actually are all spaced in 1 meter, so you can see that all these girders, this one is the girder, so this one is also the girders. So each of the point load is actually equal to 7.2 kN because actually each of the support reaction is equal to 7.2. That means on the bottom of the beam actually there's a load of 7.2 kN applied on the top of the girder. So you can see that as the beam are spaced at the 1 meter, so each of them are actually applied a load of 7.2 kN on the top of the girder. Now on the edge of the girder, you can see that actually just carrying half of the distance, because for each beam actually carry out the loads of 1 meter. However, for the edge of the beam, it just carry out the width of 0.5 meter. So as the loaded width is smaller or just half, so you can see that the load applied at the edge of the girder is just equal to 3.6 kN. So if you add all the loads together, they are totally 11. You can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are actually 11 7.2 kN point loads applied on the beam. So you have totally 7.2 times 11, and then you have two 3.6 kN at the edge. So you have 2 times 3.6. This is the total load right here, applied on the top of the girder. And then if you divide it by 2, that means it is both simply supported on both ends. Then actually it is equal to 33.2 kN, because they are simply supported on both sides of the girder. And then to find the shear and the moment at this location, you just cut a section here and then use equilibrium equations. So for here, you have 33.2 kN, and then you cut a section here, and then we try to find what is the shear force and the moment here. But remember, when you cut the section, always draw your shear force and then the bending moment in their positive direction. For shear, it points downward because you can turn this section into clockwise direction. And then for moment, it makes the structure happy, so it should be a concave downward. I mean, the direction of the moment should cause the concrete to bend concave downward. Then we can use the equilibrium equation to find out what is the shear force and then the bending moment at that particular location. Sorry that sometimes it will show some strange symbol here. It should be pointing upward here, and then this is the epsilon Fy. So you have a 43.2 kN going upward, and then you can have 3.6, and then 27.2 going downward. And then don't forget this VC. So from here, we can find the VC is equal to 25.2 kN. The answer is positive. That means the assumed direction is correct. And then again, you can use summation of moment is equal to 0. And then you have this MC here. This is counterclockwise, so it is positive. So you have 7.2 times 0.4 as the first moment. And then you have 7.2 times 1.4, then this is the second moment. Then you have 3.6 times the moment arm 2.4, then this is the third moment. And then don't forget this 43.2 times the moment arm 1.2, and then it is clockwise direction, so it is a negative moment. Then you just add them together, and then you can find that the moment is equal to 30.2 kNm. So don't worry about the question mark. Actually, if you take a note to your notes, actually those question mark will disappear. Just the program cannot show the PowerPoint correctly, so don't worry too much. The question mark actually does not appear in your notes that I have put on in the Moodle. Okay. Okay, then, well, after talking about the shear and then the moment is a specified point, we can mention about the shear and moment function. Now, usually when we design the beam structures, actually, usually we need to know about the shear and the moment. It is not enough for us to just know about the shear and the moment at a particular location. Actually, we need to know the values all along the beam in order to provide enough reinforcement for the section and in order to resist the applied shear and then the moment. And then for the beam design, usually the axial force is not being considered because actually for design purpose, the shear and then the bending moment is more important. And then the compression force or the axial force within the beam member basically can be negligible. Axial force become more critical for compression member like the columns. But basically for the beams, it is usually subjected to bending and subject to shear in major. So don't worry about the axial force. And then for here, to use a function to describe the shear and then the bending moment, basically we can use one function to describe the change of the shear and the moment for the whole beam if the load pattern or the type of the load is the same. However, when there's a change of the type or the magnitude of the distributed load, then we need to use another function to describe it. Then there will be the so-called discontinuity at the location where the type of the concentrated load or the magnitude of the distributed load are different. And then when there is so-called the concentrated load applied or couple moment applied at a particular location, then again, we need to use another function to describe the change of the shear in the moment. Say, for example, here you can see that for the first region AB, actually we have one kind of distributed load. And then between B and C, you can see that there's no loading right there. And then there's a point load applied at the point C. So actually we need to use one function to describe the shear force, and then one function to describe the bending moment at the section AB. And then we need to use another function to describe the change of the shear at the section 2. And then we need another function to describe the change of the moment at section 2 as well. And then we need the third function to describe the change of the shear and the change of the moment at the section 3 as well. So totally there will be 3 function for shear and then 3 function for moment for this particular beam. Okay. Another way how we can find that is actually we will cut the section 3 times. First of all, we will cut within the section 1, and then the second time we will cut within the section 2, and then the third time we will cut the section within the section 3, in order to find 3 functions for shear and then 3 functions for moment. And then to find the so-called functions for the shear and then the moment, first of all, again, we need to find the support reactions. And then, well, we need to solve all the external forces into components. Say if we have an inclined force, we need to solve it into horizontal and vertical component. And then again, we need to separate the coordinate using different origins. And then we need to distinguish the discontinuity of different functions. And then we need to cut the section at different sections if required. And then again, well, we can assume the distance at an arbitrary distance within the first sections, and then indicate that it is equal to x. And then again, we will use our equilibrium equations to find for the answer. Then we can use the so-called summation Fy is equal to 0, and then summation of moment equal to 0 to find the shear force and then the moment functions. To check the validity of the shear force and then the bending moment function, actually we can use this relationship. dm dx is equal to v, and then dv dx is equal to w. The physical meaning is that dm dx is actually the slope of the bending moment diagram. Equals to the shear force value. And then the slope of the shear force diagram is actually equals to the distributed load applied on the structure. Now I will have some example for you later, and then you just need to know about the relationship among the shear force and then the bending moment, the distributed load, and then the shear force. So here, first of all, I would like to discuss about an example with you, which is to determine the shear and then the moment in the beam, and then as a function of x. So as you can see here, the low pattern is actually a triangular low, and then the low pattern actually does not change. So for this function, actually, we just need one function to describe the shear force and then the bending moment. But for here, actually, we need to find the support shear and then the support moment first, before we can find for the function for shear and then for the moment. Right here, you know that actually we have 30 km per meter right here, and then the total length for the beam is equal to 9 meters. So the load actually applied to the beam, actually the resultant force is actually the area of the triangle. The area of the triangle is actually equal to 30 times the 9 and then divided by 2. Then if you like that, have the values like that, actually it is equal to 135 kN. So the total load actually due to this distributor load is equal to 135. And then this load should apply the centroid of the distributor load. So for a triangle, the centroid is equal to 2/3 of the length of the triangle. So if the base length is equal to L, then the location of the centroid is equal to 2/3 of the total length, okay? So for here, you can see that the values is equal to 135 for shear, because when you are going downward is 135. For equilibrium, you have to have the shear is equal to 135 as well. And then for the bending moment, actually you can see that the distance or the moment arm is equal to 6 times 135. Then the total value is equal to 810 kNm. So in order to be in equilibrium, you should have 810 kNm here to make the structures to be in equilibrium, right? So you have the support ends, shear, and then the moment. And afterward, you can find out the functions by cutting an arbitrary section with a distance of x. Well, to do that, actually, you also need to know what is the loading applied at the location x. So right here, assume that the length of the section is equal to 9 meters. And then this is the distributor load. And then the value is equal to 30 in this case. Then assume that this is actually the distance x here. And then this is the value that we want to find. Then we can use the so-called similar triangle to find the magnitude of the distributor load right there. So we don't know the value, and then using similar triangle is the question mark divided by 30, which is equal to x divided by 9. Okay, this is the similar triangle. Great. So we can transfer or put the term on the other side, right here, and then we can all divided by 3. So it is equal to 10 divided by 3x. So right here, you can see that the distributor load is equal to 10x divided by 3. If you want to find the total load right here, it's actually the area of this triangle. And then the area of this triangle is actually the base length times the vertical height and then times divided by 2. So this is actually the area of this triangle. And then the total load should add at the centroid of the triangle. So here on the left-hand side is 2/3 of the length of the triangle. And on the right-hand side is x divided by 3. So right here, you can see that it is a half times 10x divided by 3x here. Then, well, here you can find out the shear function by using summation Fy is equal to 0. Again, don't worry too much because this question mark is pointing upward, and then this is summation. And this is just the blanket here. So 135 is actually the support reaction pointing upward. And then this one is actually the area of the triangle, which is actually the total load applied downward. Okay. And then don't forget you have the V here. This is the shear that we want to find because you want to find the shear function along the beam. So from here, if you rearranging the term, you can find the shear function is equal to 135 minus 1.6676 squared. And then again, this question mark is actually the blanket. And then again, 810 is the bending moment. This is the bending moment here. And then 135x is actually equals to the shear force times the distance. And then the loading is right here, 10x over 3 times x. And then divided by 2 is actually the area of the triangle. Or this is actually the total force applied on the top of the beam. And then times the moment arm here, x over 3 is actually the moment arm. And then it is equal to the counterclockwise moment. And then don't forget the m here. Well, actually, we are taking moment at this location. Then the overall value should be equal to 0, right? Then you can see that the moment function is equal to 810 plus 135x minus 0.55x cubed. Well, to check the validity or to check whether it is correct or not, you can just use the differentiation dm over dx to be equal to v. By differentiating the moment function, you can check that whether you can get the shear function. And then for our case here, if you differentiate the moment function, you will get your shear function. That means actually your answer is correct. And then for here, we have another beam for you. You can see that one part of the beam is subjected to the distributed load, and then there's no loading at the remaining locations. So first of all, we can say that we need to divide our beam into 2 sections. For the first section, actually it is from 0 to 3.6 meter. And then for the second location, actually it is 3.6 meter to the 6 meter. That means actually we need to consider that there should be 2 functions to describe the change of the shear force, and there should be 2 moments to consider, 2 functions to describe the change of the moment along the beam. So that's why we need to create 2 functions for shear and then 2 functions for the moment. So from here, again, first of all, we need to find the support reactions. And then you can see that we have 50 kN per meter is the applied load on the top of the beam. So if you have 50 and then you times 3.6, actually it is the total load. It is equal to 180 kN here. And then at the ends of the beam, it is equal to 300 kN pointing downward. And then there's a couple moment equal to 150 kNm. Consider the equilibrium when it is going downward. You can see that the downward load, total load is equal to 180 kN plus 300 kN. So totally it is 480 kN. Then on the support side, actually you have to have the support reaction 480 kN pointing upward. And then for the bending moment, actually you have the moment equal to 180 kN times 1.8, and then you have 300 kN times 6 meter, and then you also have 150 kNm. You add all of them together, and then you have to have the so-called the values 2,274 kNm to resist the applied moment. So right here, you need to cut the section into two parts. As I mentioned, from 0 to 3.6 meter, you should cut 1 times. So for here, you can see that it cut at this location. It is within 0 to 3.6 meter. So you cut your first time here. And then for the second one, actually it is from 3.6 meter to 6 meter. You need to cut another section here. So for here, actually, it just cut at this location. Just cut through here, and then you have another section here. This is equal to X, and the first one is also equal to X. So remember to cut both sections in order to expose all the internal force and then use equilibrium equations to find the functions. But if you cut at the first section here, because the distributed load is equal to 50 kN per meter, so it is equal to 50 times x1, then your support reaction is equal to 480 kN pointing upward, and then you have the bending moment is counterclockwise moment is equal to 2,274, while the shear force on the right hand side is V pointing downward, and then M is actually having concave downward structures. Okay, so you consider summation Fy is equal to 0. So you have 480 pointing upward, and then negative 50 x1 pointing downward. And then V here is pointing downward, and then from here you can get your shear function as 480 minus 50 x1. And then for this section, you will take your moment on the right hand side. So you have 2274 as the first moment, and then you have 480 times x1, which is in clockwise sense, actually it is contributed by the support shear. And then the loading is equal to 50 times x1, and then the moment arm is equal to x1 divided by 2. Actually, it is in counterclockwise sense, so it is a positive value. And then you will have the M here on the right-hand side. So totally, you can see that this is the total moment. And then by rearranging the terms, actually you can get your moment function like that. It is equal to negative 2274 plus 480 x1 and then minus 25 x1 squared. Then to check the validity of the bending moment function and then the shear function, you just differentiate the moment function. And then you can see that actually by differentiating the moment function, you can get the shear function exactly the same. This one, when you have your differentiation, it is the same. Okay. And then afterward, you can consider the second part of the beam, which is actually in between 3.6 meter and the 6 meter here. And then you can see that again, you consider the vertical force equilibrium. You have 480 on the left-hand side, and then 180 kN in the middle. And then afterward, on the right-hand side is negative V here. So from here, you can see that the V is equal to 300. That means within the section, 3.6 meter to 6 meter, the shear is a constant. Okay, it is equal to 300 kN. And then we take moment on the right-hand side. And then you can see that the moment is equal to 2274 first, and then the shear force is equal to 480, and then times the distance x2. They can cause the clockwise moment, so it is a negative value here. And then you have your 180, and then you take the moment arm equal to x2 minus 1.8. So it is here. And then don't forget your internal moment, which is equal to m. So you will have all the component or all the shear force and then the moment writing here. And then you can find that the moment is equal to 300x and then minus 1950. If you differentiate this value again, then you will get V is equal to 300, okay? So actually you can find the answer of the shear force function like this from the moment function. So again, you can check the validity of your shear force and then the bending moment function, okay? If you cannot get the answer, there must be something wrong either in the shear force diagram or the bending moment diagram. Not the diagrams, the functions, okay? Agree? Okay, then we can further extend our idea to shear force and the bending moment diagram of a beam. You should have learned that already. Well, basically how to describe the shear force and then the bending moment relationship, actually we just expressed that before. dm over dx actually is equal to v, and then dm dv dx actually is equal to w. Okay. Here is actually the way how we can derive our relationship. For this, actually, we just consider a very small element here, a small element here, and then we just take it out, and then we can see that actually this is the small element subjected to the distributed load. We can call it as the W. And then assume that on the left-hand side, we have the shear and then the moment like this. Actually, it is in their positive direction. And on the right-hand side, we know that there will also be shear and then the moment. But we don't know whether there will be change of the shear and then the moment. So we just add the delta M and then the delta V there, okay? And then for the distributed load right here is equal to WX. Well, we assume the width of the small element is equal to delta X. So the total load is equal to WX times the delta X. And then the location of this resultant force is actually equal to epsilon delta X. We are not sure about whether it must be at the center or not, because if it is a constant load, then the resultant force must locate at the center. But otherwise, actually, it will be away from the center of the distributed load or the central of the shape, right? So for that one, actually, we will use the so-called the equilibrium equations to consider the case. Again, we will use a summation going upward as a positive. And then as you can see here, we will have V here, and then we have V plus delta V here, and then we have this WX times the delta X as the vertical forces. So you can see that we put all the things here, and then we will eliminate the V here. So finally, we will have this relationship. Actually, that means we have dV dx actually equal to the W. That means the distributed load is actually equals to the shear force, the slope of the shear force diagram. And then for the bending moment, actually, again, we can treat the counterclockwise as positive. And then for here, you can see that we can take moment on the right-hand side here. And then you have your moment here. This is your moment here. Actually, it is in a clockwise sense. And then for M plus delta M, actually, it is in counterclockwise sense. And then this shear here, it times delta X, actually, it is equal to a clockwise moment. So it is a negative value. And don't forget this applied load, Wx times delta X with a moment arm equal to epsilon delta X. So this one is actually the moment created by the external load. It is Wx times the delta X. This is actually the force, and then times the moment arm. which is equal to 0. So this m can be eliminated with each other. And then finally, you have this kind of function. Now remember that delta x is very small because we consider that it is a very small element. So this one is very small. When something small times something small, this one can be negligible because delta x is very small, and then you times the square of two very small things, it tends to equal to 0. So we have a dm over dx is equal to v again. So that's why we saying that the moment of the bending moment diagram, I mean the slope of the bending moment diagram is equal to the shear force. So here is actually the relationship between the shear force and then the distributed load, and then the bending moment and then the shear force. Well, or in turn, actually, we can have the integration for the relationship above, and then we have the following relationship. Again, the question mark means the integration. Integration, we can in term see at the area. So here, the physical meaning is that the change of the shear, delta is the change. But the shear force is actually equal to the area under the distributed load. Right? And then similarly, actually the change of the bending moment, change of moment, actually it is equal to the area under the shear force diagram. So that's why actually it is different, okay? Is the shear force change of the shear, which is actually equal to the area under the distributed load. And the change of the moment is actually equal to the area under the shear force diagram. Actually, these two relationships are very useful. And then you can draw the shear force and the bending moment diagram by using this concept without using the moment and the shear functions, okay? So this one is very, very convenient. And then you have to make use of that and then to draft the shear force and then the bending moment diagram. This is very important as a civil and a structural engineers. Because usually when you go for interview, this one usually is one of the questions being asked to draft or to roughly draw the shear force and then the bending moment diagram. Okay, when there's applied load right here, saying that if you have a concentrated force applied on the top of the structures, you can say that, see that for equilibrium, right here, this is F, and then you have V here, you have V plus delta V here. That means if you consider summation Fy is equal to 0, then you have V is pointing upward, minus F is here, and then minus V plus delta V here, which is equal to 0. So you can see that F actually is equal to, delta V is equal to minus F. So that means if you apply the load going downward, the change of the shear must be also a negative value. So if your force is going downward, then there will be a negative values of your shear force at the same time. If your force is pointing upward, then the change of the shear will also be positive. So you will follow the direction of the applied force. If you have a force pointing downward like 10 kN, and then at that particular location for concentrated load, your shear force will drop for 10 kN. If you have a concentrated load pointing upward, then at that particular location, your shear force will increase for 10 kN, okay? This is the way. how we draw the shear force diagram if there is a concentrated load. And then for location, if you have a concentrated moment, or we can call couple moment, if it is a clockwise value, you can see that, well, your moment will be something like that, will be acting in the counterclockwise sense. So you will actually react like that. So if you have a clockwise moment applied at that particular location, then actually there will be an increase of the moment in a positive sense, okay? Because it will act in, well, the concave downward, make the structure happy, right? So it is a positive moment. So when you have a clockwise moment, then actually it will create an increase of the bending moment, okay, in the bending moment diagram. So this one actually is quite straightforward. And then we can take a look of the way how to draw the shear force and the bending moment diagram without using a function of shear force and the bending moment. For here, I ask you to draw the shear and then the moment diagram for the beam. So this is 9 meters, and then the distributed load is equal to 20 kNm at the ends of the beam. So first of all, you can use the equilibrium equation to find the support reaction first. So for here, actually, you have found that already. It is equal to 30 kN and then equal to 60 kN. Well, if you use the so-called equilibrium equation, you can find the location where the shear force is equal to 0. Why I'm saying that? Because actually, if I draw the shear force diagram, this is the line here. And then at the first, I have 30 kN pointing upward. So to draw the shear force diagram, I need to follow there's a 30 kN going upward. And then you can see that the distributed load is actually a negative value here. Now, when it is pointing downward, actually it is a negative value. And then when it is pointing upward, it is a positive value for the distributed load. So you can see that the first it is 0. And then it is a small negative values for the distributed load. And then more negative, more and more negative, very negative, very, very negative, and super negative, okay? So right here, you know that the slope is actually positive in this direction and negative in this direction. So at the first, the slope is equal to 0, and then more and more negative, and then more and more negative. And then finally, it is very negative at the ends. So you can see that the slope is 0 here, more negative, more and more negative, very negative, very, very negative. And then finally, at this location, there will be a force going up here, and it is equal to 0. So this one is equal to 60 kN at this location. And then for this location, actually, you can see that the shear dropped to 0 because the distributed load can compensate the applied shear at the ends, okay? So in order to find the location where the shear force is equal to 0, then assume that this distance is equal to x. Then the area of this triangle should be equal to 30 kN, right? So for here, again, we can use summation Fy is equal to 0. Then the distributed load will be equal to 30 at this one. So for here, again, this question mark is actually the bracket. And then again, for the distributed load, actually, this one is equal to x divided by 9. So the area of this triangle, this one is the area, and the x divided by 9. So this one is the area of the triangle. That means it's the values of the force. And then you have 30 minus the area of the triangle is equal to 0. That means we want to find a location where the shear force is equal to 0. And then you can find that the values of E is equal to 5.2. So this is actually the values equal to 5.2 here. Okay. So this is the, including this one, actually this is the area of the triangle. This is the base, the height of the triangle. And this is the base distance of the triangle. Then you can find the values of x is equal to 5.2 meter. And then for the bending moment, if you want to draw the bending moment, actually the shear on this side is positive. The shear on this side is negative. Okay. So you know that at this location, actually the slope is equal to 0. And then the bending moment is a positive value, smaller, and becomes 0. So you can see that your diagram will be something like that, because the slope at the first will be quite positive. It's still positive, but less positive, less and less positive, and then equal to 0. So you can see that the shear force actually is very positive, less positive, and change to 0. And then on the other side, actually, you can see that the shear force actually negative, more and more negative, and very negative at the ends. As I mentioned, the shear force is actually the slope of the bending moment diagram. So for here, this is the slope. At the first, it is equal to 0, and then more and more negative, and very negative. Okay. So it is first of all equal to 0, negative, more negative, very negative, very negative. Okay. And then if you want to know what is the moment at this location, you just cut the section here and to find the moment here, and then you can know the values here. And then this is the way how we will find the answer here. This is the moment that you cut at this location. So this distance actually is equal to 5.2. So we just need to find the moment at this location. So you can see that x is equal to 5.2 here. Then we can take moment at this location. So you have 30 times 5.2, 30 times 5.2 here. And then you have, again, this one are the bracket, actually, don't worry too much. Well, because actually this one is the total force, it is half times 20 x over 9, and then times x over 9 here. So you can see that this one is actually the area of the triangle, or this is the force. It is half times 20 times x over 9, and then times x. This is actually the force, or it is actually the area of triangle, because they are the same. And then the moment arm is actually this one, so this one is moment arm. And don't forget the M here. So you will use equilibrium, and then you can find the moment here is equal to 104. So actually this one is equal to 104 at this location. Okay. So that's how it can find the maximum moment at this location. Because for the shear force location, if it is equal to 0, then actually the bending moment will be the maximum, the same location. Because when the slope of the bending moment diagram is equal to 0, then that means actually it is the shear force is equal to 0, right? So you just need to find where the shear force is equal to 0. Then it is actually the location of maximum bending moment. And then for here, again, there are several examples. that we can find for the shear force and then for the bending moment diagram. Right here, all the support reaction have been solved, and then you can draw the shear force and then the bending moment diagram immediately. For here, actually, without going back to the answer, first of all, for the shear force diagram, you can imagine the first stage no shear force, so you start from 0, right? And then you can see that the distributed load is negative because pointing downward is negative. It is 0 and then negative, more negative, very negative, and becomes a constant negative value here. So you can see that if you want to find the shear force diagram, it is negative, more negative, and very negative here. So you can see that the slope becomes larger and larger when we go to the right-hand side, okay? And then you can see that the values is a constant afterward. So afterward, the slope will not change anymore. Now, of course, it is flat at the first, and then more and more negative. And up to this location, the slope will not change anymore, and then you will keep as a constant and go downward. And finally, it will go up like that because this one is equal to 30 kN, so this one is equal to 30. So again, this is the so-called shear force diagram. Do you agree? So from the distributed load diagram, I can draw the shear force diagram. And then from the shear force diagram, I can draw the bending moment diagram. Say you can see that this one is equal to 15. Because actually this one can make the structures to bend in concave downward. So actually it is a positive value. And then you know that actually this one is negative value for shear, and then more and more negative, very, very negative. So your bending moment will always be a negative value, right? So actually negative and more and more and more negative. And then finally, actually on the right-hand side is equal to negative 42 kNm. So actually it will be something like that. And finally, it is equal to 42 kNm. Okay, that's how we can write down or draft our shear force and then the bending moment diagram. You can see that this is the way that they will have something like that. At the first, it is negative, very negative, and it keeps the same and it goes down, which is equal to 30. And then for this one, at the first, it is equal to 15, and then the value keep to be negative, so it is negative and then to be very negative. And on this side, it is equal to 42, so you have 42 here, okay? So actually, this one is quite straightforward to draw the shear force and the bending moment diagram. Well, for the other one, actually, it is quite similar. You can see that for this one, this triangle, it is simply support the beam. So for here, it is negative value, 0, negative, and more negative. And then it is still negative, but it is becomes smaller and smaller and becomes 0, right? So this is the change of the shear force along the beam. So I can draw the shear force here. At the first, it is 9 kN on the left-hand side, so I go up for 9 kN. And then you can see that our shear force diagram is 0 here, more negative, more, and then very negative here. So here it is, the slope is 0, negative, negative, and more negative. Okay? And afterward, it is very negative, and then less and less and less and less, and becomes 0. So you will go into another direction. It is very negative, less negative, and then becomes 0 here. So this one will be something like that for the shear force diagram, okay? And then you can see that the shear force is positive here and then negative on the right-hand side. And then, as I mentioned, the bending moment diagram, I mean the slope of the bending moment diagram is equal to the shear force value. So for here, you can write down the shear force, the bending moment, because right here, the slope should be equal to 0 in the center. And then it is the positive value, and then becomes 0 at the left-hand side. And then 0 value becomes negative, and more negative on the right-hand side. Okay? So your bending moment diagram will be something like that. So you can see that actually it will be something like this. For a value, if you want to find the bending moment here, just cut the free body diagram and then find the moment at this location. Then you can find for the answer. Okay. So this is the way how you can draw the shear force and then the bending moment diagram. And then for this one, actually, you can also draw the shear force diagram quickly. Because here is go down for 75, so you go down for 75 here. And then in between, there's no force applied, so it is a constant value here. And then it asks you to go up for 235, so you just go up for 235 here. And then right here, it is 100. And then it is constant slope going downward. So it is a constant slope going downward. And then finally, it asks you to go down for 40. So this one is 40, go down for 40, okay? So this one is how you can draw the shear force diagram. Here, actually, you go up for the values of 235. So you can draw the shear force diagram like that, okay? And then for the bending moment, again, you can draw quickly. Because this one is concave downward, so actually it is a negative value, right? And actually you can find the values. This one is equal to 30, and this one is a negative value. By finding the area of here, actually it is 1.2 at the distance, and then you times the values of 75, you can find the increase of the bending moment, because the area of the shear force diagram becomes the change of the moment. And then if you use your calculator, you can use 1.2 times 75. Then actually it is equal to 90. So actually you will go down and then you will go in this way, because this one is a constant value. So it is a constant here, the bending moment. The change of the value, because this is 30, the increment of this value is equal to 90. So right here, it is equal to 120, okay? Your bending moment. And then finally, you will have the bending moment actually as positive in this direction. So actually, positive means that it is something like that. So your bending moment diagram will be something like here. And then finally, your bending moment will be equal to 0. So it will be something like this. Okay, so this is the change of the bending moment. Okay. So you can write down your case like that. Right here, you go down for 75 first. Then from here to here, you go up for 235 because you have a 235 kN to go up. You can see that your shear force will drop from 100 and 160 and then back to 40. But the slope here is a constant because this one is a constant 100 kN per meter. And then you can see that there's a drop of the value of 120. How you can get that? Actually, you can see that this is the area of the triangle, of the rectangle. And then this area actually is equal to 120 kN, right? So from here to here, you can see that actually this is the value, the change of the shear force. It is equal to 120. And then the value, actually it is a negative value. So actually, you know that it is positive slope and a negative slope in another one. So you know that it will deform or defect like this, and the value will drop from 160 to 40. And then your bending moment is actually a positive value, and then you go back to 0. Okay. So that's actually the way how you can find the shape of your bending moment diagram. Okay. Do you agree? So just get yourself familiar with this kind of drawings, as it is very basic and then very important for you as a civil engineer to draw the shear force and then the bending moment diagram. Especially when you have your interview, this one must be one of your, or not a must, but always can be one of the question type being asked, okay? And then right here, again, we have a beam for you. Actually, it is a compound beam. You can see that at the joint B, there is a hinge or pin connection. And then at A, we have a roller support. C, we have a roller support. And then E, we have a pin support. So for here, if you write down the free body diagram, you can see that there are totally 1, 2, 3, 4, 5, 6 unknown right here. 1, 2, 3, 4, 5, 6. There are 6 unknown. So here 2, 3, 4, 5, and then the 6. Okay. So there are actually 6 support reactions. And then you have 6 equilibrium equations. So by using 6 equilibrium equations, you can solve all the support reactions. After solving all the support reactions, it will be something like this. And then by consider the free body diagram of each section, then you can draw the shear force diagram. So you go up for 20, so you go up for 20 here. And then you have your distributor load on this part. So you will go down from here to here for distributor load. And the total value is 100 kN, so you have 100 kN here. And then here you can just see that your shear is 80, so you have 80 values here. And then your value becomes a constant because there's no forces in between. And then there's a 25 going downward, so you will have a 25 going downward, follow the concentrated load direction. And then you come here, and then you have 225, so you have a values of 225 going upward. And then your distributor load is right here. The distributor load is going downward, so that means it's a negative slope. So you change it from 0 slope to very negative slope, and then from very negative back to the 0 slope. And then the values of the change of the value here is actually the area of this triangle. And then you can see that you have dropped the values of 90. So the area of this triangle is actually equal to 90. Then you can draw the shear force diagram like this, okay? And then from the shear force diagram, you can write down your bending moment diagram. And as you can see here, the first, actually, you have a moment of 150. So the positive value is equal to 150. And then you can see that you have a small triangle here. So this is a positive value, so your slope is positive. And then the value here is equal to 10, I mean the area. So from here to here, you increase the area for 10. And then from here to here, you can see that your slope is negative, I mean the shear is a negative value, so you will go down, and then the area here is actually equal to 155 here. So Yes. So you will have the values of, let me calculate. Okay. Go to 180 times 4. It is equal to 160, sorry. 160 here. So you will go to 0 here because the value go to 0. And then for this area, because this is equal to 3, and then times 80 is equal to 240. So here the area is equal to 240. So you will change from 0 to 240 here. This is the change of the shear force, change of the bending moment. And then from 240, you can see that the value changed to 450. So this one actually is 2 times 105. So here is equal to 210. So the change of the value is equal to 210 here. And then you can see that all the values is a positive value. So it goes up as a positive value. And then finally it is beam support, so it changes back to the 0. So actually you can, you should be able to draw the shear force and then the bending moment diagram accordingly from the distributed load, and then draw the shear force and then the bending moment diagram finally. But this is the way how you draw the shear force and then the bending moment diagram for beam structures. Actually, you can apply the same concept to a beam, to a frame, and then to draw the shear force and then the bending moment diagram. So for here, actually, you just can treat a frame as composed of several connected members. Of course, they will connect it either in a fixed end or had the pin connections at the ends. And then we usually draw the opposite sign convention, and then always draw the moment diagram positive on the composition side of the member. Or we can say that we always draw the shear force and then the bending moment diagram separately, just treat it as a vertical beam. And then we always start our origin on the left-hand side. And I will demonstrate to you how to find the unknowns for member, and then you can draw the shear force and then the bending moment diagram accordingly. Same for this beam here. You can see that actually this is a structures like this. So how to find the member ends, shear, axial, and then the bending moment? Well, actually, you need to decompose them into several parts. Let me try it for you. Let me find out the okay, where is the notes? Okay, doesn't matter, I can draw here. Now, for the frame like this, actually you have the support reaction. You just solve 5 kN and 30 kN, okay? So for here, for this one, actually we can find the member ends like this one. We can decompose our structures like this. This one is the beam, and then I have a joint here, and then I have a beam like that. First of all, if you take a look to the support reaction, it is equal to 30 kN here. Okay, and then horizontally, we have a 15 kN applied on the structure. Now to consider it to be in equilibrium, first of all, if there's a 30 kN pointing upward, to be in equilibrium, you should have 30 kN pointing downward. Do you agree? So the summation Fy is equal to 0, okay? And then if you have a force 15 kN pointing to the left, of course, at the section here, you should have the same magnitude, 15 kN pointing to the left, right? So summation of Fx is equal to 0. And then here is equal to 1.5 meter. And then for here, it is equal to 1.8 meter. So here it's actually equal to 1.5 meter. And from here to here, actually it is equal to 1.8 meter. So if you consider the summation of moment at the ends here, so you can consider summation of moment is equal to 0. Assume that there will be a moment in this direction. Then, well, you can see that to take the moment, you have to 15 times 3.3 meter. Well, actually, this one in the clockwise sense minus the 15 times 1.8 meter. And then you have negative m is equal to 0. So for here, you can see that your moment is actually equals to 15 times 1.5. Actually, it is equal to 22.5 kN. So you should have a moment here to make your beam in equilibrium. It is equal to 22.5 kN here. So you just consider the vertical member to be in equilibrium. You just used all the equations that you have learned to write down the 3 equilibrium equations, and then you can find the shear force, axial force, and then the moment at the ends of the member. Now you have 3 members, ends, moment, axial force, and then the shear force here. And don't forget there's 25 K. So how to make it larger? And then you have 25 kN on the top. Don't forget about that. And then because this one actually recorded the action and reaction pair. If you have 30 kN pointing downward, you should have 30 kN pointing upward. They are called action and reaction pair. And then if you have 15 kN pointing to the left, you should have 15 kN pointing to the right. And then if you have a bending moment in this direction, you should have one in this direction. It's the same magnitude, okay? And then on the right-hand side of the joint, if you have 15 kN pointing to the right, you should have 15 kN pointing to the left. Okay, and then for the vertical equilibrium, you have 30 pointing to the upward, you have 25 pointing downward. To be in equilibrium, you should have 5 pointing downward. And then for the moment, actually, you have 22.5 in the counterclockwise sense. Then here you should have the same in the opposite direction to make it in equilibrium, right? And then again, for this joint on the other direction, you should have 5 pointing upward because they are action and reaction pair. And then for the one pointing here is equal to 15 kN. because an action and reaction pair. And then for the moment here, again, it is action and reaction pair. So you have 22.5 kNm. So you can see that the values here is actually the values at this location. And then for here, you have a 15 kN. Because you consider 15 is pointing to the right, and then for equilibrium, you should have 15 pointing to the left. And then you have 15 kN pointing upward. Right here, you should have 5 kN pointing downward. Okay? So that's how you can find all the member ends forces, okay? For the vertical member and then for the horizontal member. Now, after finding the member end forces, then you can treat it as a beam. First of all, you can treat it as a beam like this, and then you can treat this one is the x coordinate. And then this is the shear force and then the bending moment diagram. You can draw the shear force diagram. And then the first it is equal to 0, and then the shear force will be something like this. Go down 15 kN and then go up 15 kN, okay? So this is your shear force diagram. And then for the bending moment diagram, again, you can treat it like this. Right here, actually it is 0 at the first. And then you can see that this is a negative value. So you have a negative value here. And then for this area, you can see that it is equal to 15 and then times 1.5. So the area is equal to 22.5. So here, the values of the bending moment is equal to 22.5 for the bending moment. I draw it a bit tall. Actually, it is the same direction here. Okay, so this is the bending moment diagram for this vertical member. Do you agree? And then for the, we do not need to draw for the joint. And then we can draw the shear force diagram for the horizontal beam. So for here is the beam, I can go up for 5 kN, make it to be constant and then go downward. So the value is 5, this is a positive value. So this is the shear force diagram for the beam, okay? For the bending moment diagram, first of all, I will draw here, and then you can see that my moment is 22.5 going downward here. 22.5 is negative value. So you can see that this is a positive value and then a constant force because this one is constant. That means our slope is also constant, right? Because the shear force value is equal to the slope of the bending moment diagram. And then the area, you can see that actually it is 5 times 4.5. So the area again is equal to 22.5. So actually from here to here, the bending moment diagram, this one is 22.5 is something like this. So the bending moment diagram for the structures will be something like this. If we draw both of the members together, it will be something like that. Negative 22.5, whereas the bending moment for the first member, and the x-ray is also equal to 22.5 as the second member to draw the bending moment diagram for the frame structure. Of course, we can draw also the bending shear force diagram for the beam structures. It will be something like that, and then to be something like that. Sorry, it should be positive. It is not in this direction. I'll draw it again. It is in positive direction. Negative here. Okay. This is the shear force diagram. This is the beam structure, I mean the vertical member. This is the horizontal member, okay? Okay, so this is the shear force and then the bending moment diagram for the frame. And actually, we can extend the frame to an inclined member. If you have an inclined member, usually you will decompose it into two components. One is actually perpendicular to the beam. The other one is actually along the beam. So right here, we will decompose our loading into two. One is along the beam and the other one is perpendicular to the beam axis. So you can see that we just decompose it to two directions and then find the support reactions, I mean the unknowns at the ends of the member. Then, well, once we find the values at the ends of the member, we can draw the shear force diagram and draw the bending moment diagram respectively. And then here as well, we find the shear force 7.77 here, and then we have the distributed load here, and then we can find the values here. And then from the shear force diagram, we can find the bending moment diagram. For this one, actually, I am not going into details because this is very similar to the first example. And then we can also have another example is that the inclined member right now is the in another direction. And then again, we can decompose our forces into two directions. One is perpendicular to the members and the other one is along the member, okay? And then we can solve all the member ends shear force and then the moment. And then from the shear force and then the moment, you can see that it is 70, so it is 70 here. And then we have the distributed load, so it is a constant force, I mean constant shear. And then finally go up for 2 kN here. And then from the shear force diagram, we can draw down the bending moment diagram. And then again here, you can see that we have our shear force 2.5 here. And then right here, it goes down for 80. And then finally, you go back up to 82.5. And then from this shear force diagram, you can see that at the first, it is equal to 170 bending moment with the member ends moment. And then from the shear force, you can see that it will reduce for values of 5 because of the shear force diagram. And then finally, it will drop from 165 to 0 because this area is actually equal to 165. So this one actually are quite similar and quite straightforward. And you can take a look afterward at the home. And finally, I just would like to mention about to use the so-called the method of superposition to draw the bending moment diagram for some complex case. Now you know that actually for the simple case like the cantilever structures, like when you have a point load applied to a structures, it will be a bending moment like this. And then if you have a moment, have a constant moment applies on the structures, actually it will be a bending moment diagram like this. For distributed load, actually you will get a parabolic curve like this. And then if you have a triangular load, you have a cubic curve like this. So basically for some common loading, you know how to draw the bending moment diagram. And then for some special case, like the structures here, say for example, you have a structure like this, and then you have the loading apply on the top. It is a distributed load, and then you have a constant moment here, and then you have a support or you have a reaction or force applied here. It will be quite complicated if you are being asked to draw the shear force or the bending moment diagram. But instead of drawing the bending moment diagram using all this kind of loading, actually you can decompose it to simpler cases. Like the first one, you can assume that there's just a point load here. And then the second case is that actually there is just a couple moments at this location. Or actually you just have a distributed load at this case. Then actually you can write down or you can draw the bending moment diagram easily. So like here, for here, you can have your bending moment diagram like this immediately. You know that it will be something like that. And then for here, you will draw your bending moment diagram something like this. And then for here, for the one going down, because it is actually a distributed load, it will be something like this. So you just add the three bending moment diagram together. It will be your original, the overall bending moment diagram of the original structures. So if you encounter some very difficult cases, actually you can decompose your bending moment diagram into several cases, which is simpler. And for those, actually you can draw the bending moment diagram easily. Then you can find actually the bending moment diagram, just adding them together, and then make your life easier. Okay, make use of the concept of the so-called the superposition to decompose a more complicated case to a simpler case, and then you find the bending moment separately and then just add them together. Okay. So I think I finished the discussion or finished the chapter today for chapter 2. So let me end the record first. Just wait me for a moment. OK， 咁今日咧就會到呢度。咁喺未完個堂之前，我想問有冇同學有咩問題啊？有冇問題？有冇同學有困難？OK， 嗱，如果基本上都 OK 咧，咁我今日咧就到呢度啦，好嘛？咁個 tutorial 個 solution 咧，第一個我會放上去噶啦，即係啱啱講完嗰個。咁嗰啲講完嘅 record 我都會放上 Moodle 嘅，有問題可以隨時揾我，好嘛 ？OK， 冇問題，我哋今日到呢度啦。OK， 拜拜。係咩啊？
我想問下呢個 assignment 1會幾時出啊
？Assignment 1可能過多2堂先喎，因為你哋啱啱淨係學咗頭嗰2課啫喎，未足夠做 assignment。
我明白，好，唔該你。
OK，
拜拜。
好，拜拜。